This is section 11.5, part 3, where we're going to look at using Maple to graph some of these lovely three-dimensional curves that we get from vector-valued functions. First of all, anytime you want to graph a vector-valued function, in your Maple document, you're going to always want to start with two commands. The with vector calculus, which makes all of the vector commands available, and then also the with plots, which makes all of these plotting commands available. So start with both of those so that it recognizes vectors and your plotting commands. Now I've already typed things in here so that you don't have to watch me type. But what I'm going over right now is the curve that we graphed in example 5b from your course pack. We actually did this one by hand. Notice that the command in Maple is space curve. That allows us to plot a curve. I put the actual vector in right here. Notice the angle brackets around the vector. So this one is 3 sine t, comma 4, comma 3 cosine t. My t values are going from 0 to 2 pi. By the way, in the common symbols is where I got the pi over here. And then I set my axes to normal and my color to blue. So here's the graph that Maple gives me. And it's pretty much what I expected, right? We were in the plane y equals 4. So out here along the y-axis, if I were to kind of tip this, you can see that if I go out and look right at y equals 4, everything's right in that plane. If I look at it looking right along the y-axis, I can clearly see that this is a circle of radius 3. And again, it's centered around 4 on the y-axis. Now, if I wanted to kind of ground that a little bit, I could plot the plane that this circle exists in, that plane y equals 4. In order to get them both on the same display, I will need to use the display command. So you'll notice I actually named my curve. I gave it the name C. C colon equals. If you don't want to name it, you wouldn't have to type the C colon equals. You could have just started out with space curve. But because I want to refer to it again later, I went ahead and typed that in. In my next command, I'm going to go back and plot the plane. Remember that to plot, it's an implicit plot 3D, and I'm naming my plane P for plane. So my plane is y equals 4. I told it -5 to 5 on all three axes, and I'm graphing it in yellow. Normal axes, surface style. So here's my plane, y equals 4. Now if I want to see the circle appear in this plane, like I know it should, I can just display both C and P. And now I can really see my circle lies completely within the plane, y equals 4. All right, let's go on to example 5c. Notice that I did my with plots and my with vector calculus because I did this as a new document. I didn't do them all in the same one just to make it a little easier for us to follow. The colons suppressed that big long list, so I didn't have to see it every time. So this is 5c. Again, I'm giving it a name. I'm calling C this time my space curve. My vector valued function is 3 t squared with the angle brackets around it. Just use the less than or greater than signs to get those. This should exist in the plane x equals 3 this time. I'm graphing t from -3 to 3, normal axes in red, and here we go. Here's my x-axis. Notice there's the vertex right there at x equals 3. You can see the parabola if I look right flat at the YZ plane, but it's just shifted out so it exists in the plane x equals 3. If I want to actually see it in that plane, I can plot the plane also, right down here, calling my plane P again. Here's the implicit plot 3D, the plane x equals 3, and I graph that plane in yellow again. There it is. right out at 3 on the x-axis. And then I display both C and P together. And there we go. You can see if I forgot to put the surface in there. Let me do that. All those extra lines are distracting. In my plane, let me set the style to surface. There, now I won't have all those contour lines in there. And I'll have to execute my display again. There, that got rid of all those extra lines. And I can clearly see that that parabola lies completely within the plane, x equals 3. All right, those were the ones that had a constant for one of the components. Let's go on to example 6, where one of the components was linear. And again, I've pre-typed them, they're right here. Started out with my width plots and my width vector calculus again. And here we go. The first part, I think this is example 6a, was this helix for cosine t, for sine t, t. Graphing it as a space curve. I didn't bother to name it this time because I'm not going to do anything more with it. And for right now, I've only got my t values going from 0 to 2 pi. Set my axes to normal and my color to red. So notice here, this was one time around the helix. There's our starting point on the x-axis at x equals 4. We've gone completely around the circle one time. And if I look at this straight on, you can even kind of see it stops just a little bit above z equals 6. That's that z equal to 2 pi, 6.28. So it's one complete circle looking down on the xy plane, but stretched along the z-axis. If I'd like to see more circles, I could just change my t values. Maybe I'll go to 6 pi. And that way I should see 3 complete revolutions of the helix. And there we go. You can now see we're a little above 18 here, so 6 pi. And we've gone around once, twice, and a third time as we continue climbing that z-axis. This next one is example 6b. We've got our space curve 2 minus t, 3 cosine t, and 5 sine t. For right now, I just did one revolution from 0 to 2 pi. And here it is. If I look down, you can see that x equals 2, y equals 3. That's my starting point that we discovered. And you can start to see this go backwards along the negative x-axis, right? Negative because of the negative slope on the linear term. If I look at this straight on, it looks like a circle, but it's only because Maple changed the scale. Notice it is from -3 to 3 on the y, and from -5 to 5 on the z. I can show you how to fix that in a minute. All right, this was one complete circle going back. If I want to see more, I could change that to 6 pi. If I want to see 3 circles, again going backward in the x direction. So backward along that negative x-axis. I believe the command is axes equal constrained. Let's try that. Did I not get that right? Shoot. There's a way to make it so it doesn't rescale your axes. And I'm going to have to look that up and let you know. Sorry, I can't remember the command off the top of my head right now. Something like that anyway. I'll figure it out and let you know. All right, one more curve to look at. This was 6c in your course pack. The space curve was t, t, t squared. And we looked at this as a parabola, x equal t, y equal, or z equal t squared. And we looked at it as being stretched in the y direction. I let my t's go from 0 to 3. So you can see here there's that half a parabola. But instead of staying right in the xz plane, or even right in the x or yz plane, this has been pulled out along the positive y-axis as it goes out along the positive x. If I wanted to see the other half of the parabola, I would have to go back to some negative t values, and I could do that. There we go. Now you can see the negative t values going back along the negative y direction as well. So it's like a parabola that's been tilted 45 degrees. All right, one more. More graphs. These are the fancy ones. These are the ones that we really couldn't do by hand. You'll see again I started with my with plots and with vector calculus. This first one I like to refer to as my Pringles potato chip curve. You can see the function sine t, cosine t, sine 2t. None of the terms are constant or linear, so we wouldn't have been able to do this one by hand. And here's the graph I get. It's probably bent a little bit more than a typical Pringle, but almost looks like the outline of a Pringle to me. Sort of a saddle shape. This one's got a lovely complicated functions, this whole thing here. Clearly none of the components are linear or constant, so not one we would have done by hand. I went t equals 0 to 2 pi again. And it looks like kind of a mess from this angle. But if I look at it kind of more top down, it's almost like a coiled wire, a coiled spring, isn't it? That's been kind of brought around to meet itself, or like a slinky if you take the ends and put them together. You can kind of see from that perspective what this looks like. All right, so if you ever come across any fun curves that you want to graph in 3D, I highly recommend Maple as a good way to do that.